everyone. My name is Luca, and today I'll be presenting the role of unknowns in Julia UDE modeling. So this work was done in conjunction with Dr. Giulio Dalla Riva as my supervisor. So before we begin, we first need to talk about universal approximators. So what are universal approximators? Universal approximators are objects that are able of approximating any function to some parameter size limit. So examples of these are Chebyshev series or Fourier series. And it turns out, according to the universal approximation theorem, that any sufficiently large neural network with nonlinear activation functions is also a universal approximator for any Rn to Rm function. Okay, so now that we know that, what is a universal differential equation, or UDE? So a UDE is a differential equation of the form du over dt is equal to some known function, so some mathematical expression that we know, plus a universal approximator, which in our case is this neural network. So why do we even have UDEs in the first place? Well, suppose we have some data, and we want to find a model that represents it, that models that data, right? We want to find a differential equation that can model that data. And perhaps we have some information about that system. Perhaps we know it's periodic, or we know there is exponential growth. So we want to include that information into the model, and we do so via K. However, by doing so, we may not get a perfect fit to our data, right? There may be things that, there are like underlying mathematical things going on that we're not encapsulating with our known function, and we use a universal approximator to figure them out. But this leads us to another question. What if K, that we previously described before, what if it's incorrect? So what if we specify something mathematically that's not supposed to be in the model? Can a universal approximator, or neural network in our case, find that mistake, and can it correct it? So here we have a little example. So we generated data from the following system, Lotka-Volterra system. So we have that here. And so if we have correct specifications that we have up here, we can see that we have a really good fit when it comes to predicting data into the future. But when we include a wrong specification, so here we use K1, so this is the first, so instead of using U1, we used this is a typo here, it should be 0.2 plus 0.8 times U1. And again, if we use an incorrect specification for this equation right here, instead of using minus U2, we use 0.2 minus 0.8 U2, we get an equation that is slightly off, right? It's not quite it's not quite a perfect fit. So before we get really into it, let's talk about the methodology of this experiment. So how did we even go about conducting this experiment? Well, first we need an ODE, right? So we generated this with the following Lotka-Volterra differential equation. And we took data at a time step of 0.1 from 0 to 5, right? So this is the data that we generated. This is our true ODE. And then we define our UDE. So how did we define our UDE here? We have this kind of parameter A here that is a parameter that we can adjust to make our K more incorrect per se. I know it's not a great way to phrase it, but if A here is equal to 1, this function 1 here gets eliminated, and we're just left with the correct specification. And as we make A larger, we get a more and more incorrect specification. So we vary this parameter A, and then we train the UDE, right? We train the neural network, and we get a model. We then use symbolic regression, SYNDI, to get back a symbolic expression of our differential equation. And I should reiterate, we don't perform SYNDI on the entire model per se. We just perform SYNDI on what the neural network does. So only on this part right here, right? Only in the unknown part is where we perform the symbolic regression. We don't perform symbolic regression on the whole model overall. And this is important because you'll see that the results we get are, indicative of this. So anyways, we train the model, we perform symbolic regression, and then we make predictions from 0 to 10, again, at a time step of 0.1. We then calculate the sum of the absolute differences of our UDE and the original ODE from which we got the data, and we add them together from 5.1 to 10, again, at time steps of 0.1. So this is like to model like accuracy, right? How well did we predict the future with these equations? And so finally, we get to our solutions. So here we start off with just varying A with our function of U1 and U2 being 0. So as we can see, when we vary A ever so slightly, we get like, like very odd results. So, we got like so if we look at no error whatsoever, we get a very good fit, right? And even varying A slightly, we start getting like crazy results. So basically, moral of the story is no. If you have incorrect specifications, your UDE won't necessarily be able to fix those mistakes. And again, I want to reiterate, they could be fixed if we applied symbolic regression on the whole model instead of just what the neural network finds. So I just want to reiterate, perhaps we could get different results and perhaps better results if we did perform that way. But unfortunately, with the way we had conducted the experiment, the answer is no. We got like horrendous results. However, it's not all bad, as we can see. Like over here, we have like decent-ish results, decent fit. And actually, this is the example we have right here. So as we can see, it's not entirely bad, but again, it's not entirely good either. And then finally, we have unbounded. So basically, this is like our solutions just shot up to positive or negative infinity to the point where basically like our solutions were unbounded. Like we got like crazy results. And yeah, so these were the results we got. Thank you very much. That's all I have for today.
So I was a little confused about the setup that, and I'm sure this is just not familiar with the area, but you have your sort of correct solution and then this incorrect additive term.
Yes.
So it seems, without having a deep understanding of it, it seems like you would be training the neural network to learn that additive term.
Well, you're training the neural network to kind of try to cancel that term, right? So let's say, let's say we have, so let's look at this example right here. We have, so for anyone wondering, the question was if the neural network, if we give it a wrong specification, would the neural network learn the wrong specification? And so the answer to that is ideally no. So here we have a correct specification, and so we want our neural network to find this term right here, right? So if we give this specification here that is incorrect, ideally what we want the network to find is this term here, then we want it to minus 0.1, and we want it to add 0.2 U1, right? So we want it to make that correction. But the problem is it usually does a good job. So if you train the UDE numerically, usually the result is okay. The problem is when you then do the symbolic regression, since we're only doing the symbolic regression on the neural network, the incorrect term stays in our equation. So that's why I was saying it's important that if you were to perform symbolic regression, you perform it on the function as a whole, because then in that case, you might actually get rid of these terms here. But yes, with the way we had conducted the experiment, that wasn't the case. Yeah. Any other?
I'm sorry.
Yeah.
Is it a limitation of the neural network learning? Is it a limitation of symbolic regression? Is it like because of the order that, like what is the? The error usually was with the symbolic regression. So the neural network as a whole, they're not great when it comes to predictions, but they're really good at like getting a really good fit for the training data. They're not really good for the testing data necessarily. But with usually the problem is with the symbolic regression, because the symbolic regression, that's when you start getting like, you start getting terms that are relevant, like your coefficients of U1, your coefficients of U2, et cetera, et cetera. So yeah, it's a bit of a mixture of both. For most of these experiments, we got a really good fit on the training process. Only I think on like one case of the unbounded, like instead of 10 to the negative 6, it was like 10 to the negative 5. But like we got really good like losses overall. So if I had to guess, I think the error, the mistake is more to do with Cindy more so than it is with the neural networks. Yeah. No worries. Yes. So like for Cindy, it's supposed to be.
No, I haven't actually. Yes. We didn't adjust that parameter. No. We stuck with, I think it was 10 to the minus 3. 10 to the minus 3 or something. But yeah, no, we didn't play with that parameter. So again, yeah, absolutely, playing with that parameter. And there's a lot of things that actually can be varied here. So it's not, this isn't like an experiment to say, this is, how it is. It's more as like an indication of like, these are things you might want to consider next time you want to do the experiment or, solve a UDE. Yeah.